This is the third of 3 videos on how to use Newton's gravitational equation to deal with problems involving gravitational force between two masses. The first video deals with gravitational field strength and mass versus weight. The second video deals with the universal gravitational equation, what it means, and a couple of proofs for it. And this particular video deals with how to use the universal gravitational equation to solve some problem. So let's take a look at the problems. The first one is about 2 young people sitting on a park bench. They're 0.5 meters apart, center to center. One person has a mass of 65 kilograms, while the other person has a mass of 55 kilograms. It says here they feel some attraction towards each other. That is, they are attracted, and we want to find out if this is the force of gravity or not. So the equation, as is, says that force of gravity between two objects is given by the formula of G, universal gravitational constant, times mass, divided by the distance between the two objects squared. G is a universal constant. It will never change. The mass of one object is 65 kilograms. The mass of the other object is 55 kilograms. And we're going to divide this by the distance between them, which is going to be 0.50 squared. So you got to put this in your calculator correctly. Make sure you use the right button to get this in properly and work it out. If you do the arithmetic on your calculator, you'll get 9.5 times 10 to the minus 7 newtons. So if they are feeling this mutual attraction towards each other, it probably isn't the force of gravity. This is much too small. It's less than a millionth of a newton of force, and probably the frictional force between the bottoms and the fourth bench will keep them where they're sitting. Okay, there's another example then, example 2. And this time we have 2 large supertankers, each having a mass of 1.6 times 10 to the 8 kilograms. And they're sitting 225 meters center apart. We want to calculate the force of attraction this time. So once again, force of gravitational attraction is going to be equal to GMM all over R squared. So the gravitational constant does not change. It is a universal constant. It is always the same number. Mass of one object is 1.6 times 10 to the 8. The mass of the other object is identical at 1.6 times 10 to the 8. Or you could have squared this. It wouldn't make any difference. Divided by the distance between them. And again, don't forget to square it onto here. So once again, you could calculate out, put the numbers in correctly, using exponential numbers in here, work it out, and you should come up with 34 newtons of mutual force. A lot bigger than this, but when you look at the mass of the supertanker here, it probably isn't a very significant amount as well. Okay, so let's take something even bigger. How much bigger? Well, how about the Earth? Now I got to change this, okay? I put the wrong number in here. This is not supposed to be 5.8. It's 5.98 if you want to be exact, okay? Times 10 to the 24th. Mass of the moon, and we know that they're this far apart. And again, let's calculate the gravitational force of attraction between them. Once again, same equation. Force gravity is GMM all over R squared. So gravitational constant does not change. It's always the same. The mass of the Earth is 5.98 times 10 to the 24th, and we multiply by the mass of the moon, 7.4 times 10 to the 22nd, and we divide that by the distance between them, 3.84 times 10 to the 5th, by the way, so 384,000 kilometers away. Don't forget to square that. Now, these are some big numbers. Be careful when you put them into your calculator. You can do it. If you do this, you will get a force of approximately 195, one too many sig figs, but that's okay, times 10 to the 20th newtons. Finally, we have a significant amount of force, and we should have. It is this force that keeps the Earth and moon rotating about a common center. Now, we look as a moon go around the Earth, but they're going about a common center onto here. Okay, so now that we understand that, let's take a look at this. It says, let's calculate, going in here, F equals ma to calculate acceleration due to gravity at the moon's location near the Earth's gravitational field. In other words, we're going to calculate the G field strength. Now the G field strength, G, I'll get a purple out of here, is going to be equal to the force that we have divided by the mass of a moon. Now the force is going to be this answer, 1.95 times 10 to the 20th newtons. The mass would be the mass of the moon. That's what we're interested in to hear, the force of gravity on the moon. So we're going to go 7, on the moon by the Earth, right? 7.4 times 10 to the 22nd, put it on the bottom, work it out, and you're going to get 2.6 times 10 to the minus 3 newtons per kilogram, or if you prefer, meters per second squared. They're identical units and mean exactly the same thing in here, which is a pretty small number. The acceleration of the moon is not very big. This was absolutely crucial because Newton knew that he could calculate the acceleration of the moon around the Earth by using the period of the moon and knowing the distance from the moon to the Earth. He could calculate that, and he did that and come up with this number. Now, if you look at that number, you see that that number and that number are essentially the same. He realized that he was on the right track when you can get the same answer of the acceleration from two different ways. He knows that his answer is really in the ballpark into here. Okay, so let's take a look at this problem into here now. We want to find out what would a person weigh if he went to the surface of Mars. And the only information I give you is the weight on Earth. Now that's important. We can get the person's mass if we know what his weight is. Remember, weight is force of gravity. And if we divide that by the acceleration of gravity. Now we know that his weight is 650 newtons. We know the acceleration of gravity near the Earth's surface is 9.81. So if we divide the two, we will get 66.3 kilograms of mass for this person. Remember, the mass doesn't change where you go. So we can now use this to calculate the weight of the person on Mars. Weight equals force of gravity you can get by going GMM all over r squared. Well, this time we're going to use the acceleration of the universal constant of 6.67 times 10 to the minus 11, the mass of Mars, 6.42 times 10 to the 23rd, the mass of this person, 66.3 kilograms, and we're going to divide it by the radius of Mars because we know what the force will be on the surface of Mars. So 3.38 times 10 to the 6. We're going to square that, and if we do that, we'll come up with a weight of 248 newtons on Mars. Easily do on this way. The last example is going to be taking the universal gravitation and rearrange it. So two objects. There's one. There's the other. They should say identical, otherwise we can't solve this problem. So they are two identical objects, initially 125 meters apart in space. They feel a force of 0.035 newtons, and we want to know what is the mass of these two things. Okay, so a little algebra. Force equals GMM all over r squared. Since it's the same mass, the force will equal gm squared all over r squared because the same mass is in there. Bring the r up, so you can get force times r squared equals gm squared. Bring the g down, so I'm going to go up here, and I'm going to get m squared is going to equal to force times radius squared all over g. And finally, the last one, mass will equal the square root of the force times the radius squared divided by g. So if we put everything in now, we should be able to get it. The force is going to be 0.035. The distance between them is 125 squared, and the universal gravitational constant is 6.67 times 10 to the minus 11. So when we work that out, again, work out your calculator, you will come up with a mass of about 2.9 times 10 to the 6 kilograms, right like that. And about the size of a couple of boulders that are in here. So a little bit of algebra, get to the answers. And then final question here, what would happen to the two masses? Well, they're basically going to move together. And this is in fact how our stars are formed. Little bits of massive hydrogen sitting in space are being attracted to each other by gravity. They clump together. As more and more clump together, they become big enough to start nuclear fusion, and voila, you have a star formed that's here. Okay, so I'd like you to go on to the worksheet now to practice the concepts that we just talked about right in here. So take it out and work on it.